Hello and welcome again to my Physics Online video lecture series. Today's video we're going to be discussing interference from multiple slits. So at this point we have already discussed, and before coming to this video you should have gone to and watched the videos discussing the double slit experiment, Young's double slit, where to find the minima, what the interference pattern looks like, etc. Optionally, you may also want to watch the video about single slit diffraction. However, that one is not strictly necessary for this video. I'm mostly just going to be focusing on the slits as independent sources and neglecting diffraction effects, and just looking at how they would interfere with each other if there's more than two. So before we can get to that, we need to kind of recall some of the key results from the double slit. And not just results, but parameters. So in some sense, the main results are: where are the intensity maxima, where are the intensity minima, and what are the parameters, and how did we find these locations for max and min. All right, the maxima locations are given by the equation d times the sine of theta is equal to the order n times the wavelength lambda. And the minima says that d times the sine of theta is equal to n plus or minus 1/2 times lambda. So recall that n is an integer value, so any integer, and it stands for order of maxima. Now n itself must be an integer because it is an order number. It is a cardinal number, but it goes with ordination of, or ordering of, the maxima and minima. N equals 0 is actually the central, and then n equals 1, 2, 3 is basically how many do you have to count away from that center. Now n can be negative because we can go to the left or to the right or above or below depending on your orientation, but it does need to be an integer. Lambda, of course, is the wavelength of your light, and we're kind of assuming here that you have monochromatic light, so it all has the same wavelength. Theta is the actual angular position. So when we say where is it located, we're talking what's the value of theta. D comes from the slit separation. So if I made a little diagram in which I have a couple of slits in sort of like a slit mask, and then somewhere else I have a screen, and I draw a line perpendicular to the slit mask, and then I want to find what is happening at some point P, then that point P is located at the angle theta, which subtends that normal line and the line that begins at the normal line and ends at P. So the n equals 0 maxima occurs at theta equals 0. And then there will tend to be additional maxima above and below. So here might be n equals 1, here might be n equals 2, somewhere up here might be n equals 3, and then below it, but equal distant from it, I should have a -1, a -2, and a -3, etc. Distance d is the distance between the two slits. So if I take this distance between the two openings, that is distance d. And you'll recall that we figured out all this by making arguments from phase differences between light that traveled from the top slit to a given location and from the bottom slit to a given location. The basic rule was that if the difference in phase was equal to an integer number times pi, then the times 2 pi, then the two should be in phase with each other, and thus we should get a local maximum. And if there's a difference of a half of a wavelength, which is equivalent to a phase difference of pi, so the path length difference is lambda over 2, or 3 lambda over 2, or something like that, and therefore you have pi, or 3 pi, or 5 pi, or etc., then the two waves cancel and you end up with no light arriving at that location. And so you have an interference minimum. So the question is, what happens if we add more slits? So let's draw for ourselves a diagram to think about what would happen if we were to add a third slit to all of this. And we can make the slits continue to have a separation distance of d between consecutive slits or between outside slits, and therefore d over 2 to the middle slit. We do get slightly different results because of how we're defining d in this case. But now let's consider a location over here on our screen. So I draw a nice big screen. Let's consider a location right here. We ask, how far does light have to travel from each slit to arrive at this location? We might also ask, what happens for different phase relationships? Okay, so let's say that I have light that's incident from slit number 1 to this location. I have light incident from slit number 2 to the same location, and I have light incident from slit number 3, again, to the same location. So we're going to have different phase differences between these. Let's call d the distance between two consecutive slits as we did before. So this distance is d, but this distance right here is also d. Okay, now let's say, for the sake of argument, that light from all three of these, and again I could maybe define this to be angle theta, and this would likewise be angle theta, this would likewise be angle theta. Let's say that light from all three of these arrives in such a way that they are all in phase with each other. In other words, it takes maybe one extra wavelength from this slit to arrive at this location compared to this one, and 2 from this slit compared to this one, and therefore 1 compared to this one to arrive at this location. So light from all three would be in phase. Essentially, you would have a total, E total, is equal to, and basically you would have something like E from any given slit times 1 plus cosine of 2 pi plus cosine of 4 pi. Okay, this is what it would mean for essentially like delta phi between slits. Phi 1, 2 is equal to 2 pi, and phi 1, 3 is equal to 4 pi. All right. Well, we know that the cosine of 2 pi and the cosine of 4 pi are both equal to 1, and so you'd end up with E total is equal to 3 times E slit. For the double slit, recall that that's 2 times E slit, and now recall that you have to square that number in order to get the intensity. So you'd have an intensity essentially of 9 times E slit rather than 4 times E slit at that location. That's a local maximum. Now let's consider what happens if we're off by a phase of exactly pi between the first and the second, instead of between the outer two, let's say. So a phase difference of pi, what would that do? Well, for that phase difference of pi, slit 1 and slit 2 would essentially cancel each other, just like in a double slit with a difference of pi. but you still have slit number 3 that's present. Okay, so let's write that. In this case, my E total would now be the E from each individual slit times 1 plus cosine of pi plus cosine of 2 pi. Well, cosine of pi is -1, cosine of 2 pi is +1. So the first two terms would cancel, but I'd still have +1 left. So in this case, E total will just be E for a single slit, essentially. Notice that that's not 0. So is it possible to make these come out to 0? Well, yes, actually. For example, if I make the first cosine term be 1, or in other words, the first term is 1, and the second term is, let's say, -1/2, and the third term is also -1/2, that would actually do it. Okay. I might also have 1, -1, and 0. That would also allow for this to occur. So now we ask, is it possible to make either of those things occur? And the answer is yes, it is possible. We can have the following phase difference. Suppose that the phase difference between slits 1 and 2 is pi/2, and between 1 and 3 you have pi. Well, now my total, E total, will look like, for a single, times essentially 1 plus cosine of pi/2, which is 0, plus cosine of pi, which is -1. So this is -1, this is 0. Well, now I have 1 plus 0 minus 1, which is 0. This one gives me a total of 0. So I still have a local minimum at 0. Now it turns out that there's another location at which the phases can balance to 0 as well. And that other location is essentially going to be midway between the location where these phases went to 1, which is right here, which is where you have a difference of pi between everything, and where they hit their next maximum, which was this top case, 2 pi difference. Okay, so if I were to do that, that essentially means that I expect if delta of phi 1, 2 is 3 pi/2, then that would imply that delta phi 1, 3 is twice that much, which is 3 pi. And so for that location, my total would be E single times 1 plus cosine of 3 pi/2, that's 0, so this term is 0, plus cosine of 3 pi, and that term, of course, has a value of -1. And so here my total is again 0. Okay, so this new pattern with 3 slits, rather than being a simple sinusoidal or cosinusoidal pattern, now has sort of primary and secondary maximal values. So remember again that intensity total is proportional to the square of the total E field. So if I wanted to plot my total here versus, let's say, theta, at theta equals 0, I have locally a maximum. This falls off to 0 and then rises back up and then falls back to 0 again, and then rises back up to the maximum, falls down here to 0, rises, etc. From our previous discussion, figuring out what the E field strength is for each of these locations, where we have 3 ES, 1 ES, or 0 ES, we can kind of label on this one. Remember, we got to square everything, so 3 squared is 9. Let's say I slit. And this location right here, it's not drawn entirely to scale. I've blown it up a little bit just to show. This would be 1 times I for a single slit. And then these two locations are both zeros. And where are they occurring? Well, basically you're occurring at locations where theta over here is such that this phase difference is 2 pi at this location between two slits. So now we go back and we ask, what is it that theta is equal to in terms of all that? Well, remember that for a double slit, delta phi between two slits was equal to 2 pi times the distance, basically the path length distance, which we could call delta L or delta X or something like that, divided by the wavelength. Alright, so we're looking at a delta phi being equal to 2 pi at this location, being equal to pi over 2. Sorry, this one is 2 pi. This one right here is 1 pi. This is pi over 2, and this is 3 pi over 2. So not entirely drawn to scale here, but that's where these locations are in terms of delta phi. But now we say, all right, well, in terms of theta, if we go back to our original diagram, the one that we drew over here, where you have like the double slits here, and you're ending up at a location over here, and these are more or less parallel rays, then the path length difference delta L, which is given here, in terms of this angle theta, should look like d times sine of theta is delta L. And that's why we used the d sine theta is in lambda for constructive interference, because that was the condition for constructive interference. Over here, essentially our kind of equivalent, this would be 2 pi d sine theta over lambda. And so our equivalent here is that this location was for pi, this location was for 2 pi. Primaries becomes essentially n times lambda is equal to d times sine of theta. Secondaries, these again are the primaries, and the secondary is the little peak. So this is the secondary. Secondary becomes essentially n plus a half times lambda is equal to d sine of theta. The minima are occurring at essentially n plus 1/4 or n plus 3/4 times lambda is equal to d sine theta. Okay, so that's where your minima are actually located. Now, worth noting again, we've kind of redefined for ourselves what d is. It's the distance between two consecutive slits. Some textbooks, if you're out there reading a textbook, or some internet sites or some other people, would define, and fairly, they would define d to be the distance between the two outermost slits. if you use this definition for D instead of the one that I've drawn here, you can still get the correct answer, but their definition for D is a factor of 2 larger than my definition for D. And so that alters all of these in such a way that essentially it will not work with these equations that I have here. You'd have to go through and rederive them. One thing remains in this video, which is to sort of generalize it. What happens if we have more slits? Well, more slits basically allows us to have more combinations for secondary peaks and for local minima. Essentially, the pattern is as follows. First of all, if you have n slits, let's say let's use a capital N, n slits, there will be, so we'll have n minus 1 minima, n minus 2 maxima between and these are secondary maxima, between 2 primary maxima. And the other part of the pattern is these tend to be equally spaced angle-wise for the same reasons as run through in the video so far. The other part of the pattern is that I total at a primary will tend to be basically n squared times I for a single slit, where I for a single slit is also the intensity at a local minimum. So, or at a secondary maximum. So at a secondary maximum, then you can say I total secondary is equal to IS. So if I have 4 instead of 3 slits, then I expect my intensity to be 16 times larger at a primary than at a secondary, etc. Now we can basically extend this result to having many, many, many slits, hundreds or even thousands, but that's the subject for another video. So that's all for today's video. Hopefully you learned something in it, and as always, thanks for watching.